In this part of the lecture, we want to deal with a special case. The previous cases, we had the assumption that the distribution of your x was normal. In other words, it had a bell shape. Now you are coming to a case where the distribution may have or may not have a bell shape. What do you do if you want to look for the probability? That's the problem we face, that some distributions do not have a bell shape. So we need to do something about it. Welcome to the central limit theorem that helps us solve that problem using sampling distributions. So here we are simply saying you start with an x distribution that is not bell-shaped. How do you solve the problem given that you are interested in probabilities? You come to that distribution and you take a sample greater than 30 and you calculate the average. So if you take a lot of samples, you randomly take a lot of samples of size n greater than or equal to 30, and you compute the averages and you create a distribution of the averages. Note, these are averages you've taken here. You now compute what we call a sampling distribution of sample means. It will have a normal shape. When it has a normal shape, you can now convert it to the z-score and look for probability. So for you to transform this distribution into a bell-shaped distribution, you need to take samples of size n greater than or equal to 30, a lot of them, and when you create a distribution of averages or of means, it's going to be bell-shaped. So the initial cases we had seen before this lecture, we were just looking at x that is normally shaped, that is bell-shaped. In this case, it can be bell-shaped or not bell-shaped. However, once you create a distribution, or what we call a sampling distribution of sample means, according to the central limit theorem, it's going to be bell-shaped, and then you can now convert it to the z-score and look for probabilities. That is it. Okay, let's go on. There are some properties of this new distribution. So you are starting with an x-shaped distribution, which has a particular, well, a normal distribution, which has a mean there. If you create a distribution of sample means, it's going to look normal. What I presented here, it's not normal, it will look normal. If it's already normal, it's still going to look normal. So you couldn't care less. It will end up looking normal. So this is what we are saying. Not normal and normal changes nothing. You will end up with normal distribution, and you can use it for your computation. Okay? Now, there are certain things we should know. When you do that, actually, I think I have it in the next slide or not, doesn't matter. When you do that, you will find that it has the following characteristics. The average of this new distribution will be identical to the population average of the initial one. The average of this new distribution will be identical to the initial average. So if you are told that a distribution of sample means has been created, calculate the average. There's no calculation to be done. Just use the average of the initial population distribution. On the other hand, if you are told to calculate the standard error, okay, or the standard deviation, simply do sigma, the population sigma that you had here, divided by the square root of the sample size. All these values are always given. That will give you basically the standard deviation of the distribution of sample means. Now, even if you don't understand this theory I'm talking of, once we start doing exercises, it's going to be very clear. Let's take this example. You are told that the mean is 63, standard deviation is 11, and the n, which is the sample size, is 100. Now, this is where you have to be very careful. It says find the mean and standard error. We've just said the mean of this new distribution will be identical to the initial mean. And it says, and the standard error, you simply take the standard deviation and you divide it by the square root of your n. And that's it. So let's just do that. You can see that by definition, they are the same. And when you are computing the standard deviation of the distribution of sample means, it's also called the standard error. You simply take the standard deviation, divide by root n, and that's it. So these are the first set of computations you may be asked. And we keep having similar examples where you do exactly the same. Okay, this is very similar to the previous one. Now, if we move on now, we want to see something else. In this case, you normally have an X score, but you have an X bar score because you are looking at the distribution of sample means. So in your equation, you will be using the sample mean here. You will be using the population mean, which is identical to the mean of that distribution. And you will be using the standard error. So this is how your equation will look like. This is your equation to convert to the z-score. Let's use it. So in this case, you've been told that you have an n of 50. You are looking for this particular group, 15 to 19. And you've been told that it says, what is the probability that the mean time? This is the key word. What is the probability that the mean time? Whenever you see the word the mean time, they are looking for the probability of the mean time. You know you are dealing with this formula. If it said, what is the probability that the time they spend? Then you are dealing with what we've seen in part 1, 2, and 3. But once you see what is the probability that the mean, that's it. You don't search again. You know you are dealing with the central limit theorem. Okay? If you miss that word, you will get mixed up. But if you catch this, you can never get confused because it's always about that. So you've been given two values. So you'll have to convert this to the z-score, convert that to the z-score, and go to your table, look for the probability, and deduct this smaller area from the bigger area. Now, for you to do that, you have your n value, you have the standard deviation, the mean is also given. We are talking of this age group, so if you come here, this is the age group, and this is the average. So you've been given the average, standard deviation, and n. So you want to convert this to the z-score and that to the z-score. Let's do it. So this is your equation for the first one. The second one, you now have their z-scores. You go to your table and you look for the area to the left of the first z-score, the area to the left of the second, and then you will deduct the smaller one from the bigger one, and that is your probability. So this is the only difference between what we've been doing in the previous lectures, is to determine that we are dealing with this new formula and everything else is the same. Now take this example. We've been given the mean, we've been given the standard deviation, and it says, what is the probability that a randomly selected undergraduate who is a credit card holder has a credit card balance? Note, it has not said It has not said has a mean credit card balance. It has simply said has a credit card balance. It means you will use the first formula we saw in the previous lectures because you have not seen the word mean here. So how do we proceed? We have our X score. We convert it into the Z score using this equation. Once we have the Z score, we look for the probability, and voila. Second question. Now it says, what is the probability that their mean credit card balance? Now it's not just the credit card balance, but it is the mean credit card balance. So in this case, you have to use the new formula we are talking of, not the previous one. So here, of course, you see it's also giving you n. You have to integrate everything. So how do we proceed? We are going to use this new equation whereby we just plug everything in there, obtain the z-score, and from the z-score we go to a table, obtain the area or the probability, and from that we extract what we need. Now, let's take a look at this. So what conclusions can we draw from the first case? We can see, so how do we get the 34 there? It's coming. So let me go back there. So basically it's coming from this first computation we did. So we round it to 34. And when we do the second computation, we basically have, if you round it, you can have 2. So what we are saying is that there is a 34% chance that an undergrad will have a balance less than 2,700, and there's a 2% chance that the mean of a sample of 25 will blah blah blah. That's all. And that is it for the lecture. Just play around with it and make sure you understand it. Play around with the examples, do the exercises, and have fun in the process.